Okay, let's explore something really fascinating today. Imagine patterns, right? Incredibly ordered, really intricate, but here's the twist. They never just repeat themselves.
Yeah, it's like a secret code that just keeps unfolding, always generating new arrangements, but, and this is key, always following a really strict set of rules.
Exactly. And today, in this deep dive, we're looking at something called Penrose Tilings. And the really interesting part, how these, well, seemingly abstract math patterns are acting as a kind of unique language for cutting-edge AI.
Right. Our mission here is basically to shortcut you to being well-informed on this intersection. It's pretty exciting stuff, pulling from recent research, recent articles.
We want you to see how the precise rules, the grammar governing these non-repeating patterns, are being used by AI.
And it's for everything, from designing totally new materials to making neural networks potentially much more powerful. We'll get into the specifics.
Okay, so what does this actually mean for you? Let's start at the beginning. We need to really understand what Penrose tilings are.
Their main feature, the core characteristic, is something called aperiodicity.
Aperiodicity.
And that just means these patterns, they never repeat in a simple, straightforward way, like shifting the whole thing over, even though they look perfectly ordered.
Okay, so not like regular wallpaper, which just repeats the same block over and over.
Exactly. Think of it maybe like uh, a complex piece of music. It never repeats the exact same melody, but it sounds harmonious, it sounds structured, because it's following some kind of sophisticated underlying rule set.
And like any language, these tilings have a basic vocabulary, don't they? Like the building blocks.
They do. For the classic 2D Penrose tilings, that often means two specific shapes. You might have seen the kites and darts.
Oh yeah, those ones.
Or sometimes it's two different types of rhombuses, so those shapes are kind of like the words.
But the shapes themselves aren't the whole story, right? What gives them this incredible complexity? Is it just having two shapes?
No, that's a great point. It's not just the shapes. It's their grammar, or you could call it their syntax. These are very specific matching rules about how they have to join together.
Ah, okay. So rules about which edges can touch which other edges.
Precisely. It dictates how they form these complex sentences of patterns. It's like having a strict instruction manual for Lego bricks, maybe, ensuring the wall you build never exactly repeats itself, but always looks perfectly fitted together, perfectly coherent.
So it's the rules that enforce the non-repeating part.
Absolutely. Those rules are what guarantee the periodicity of the whole tiling.
And there's a formal way to describe this grammar, isn't there? Something called L systems?
Yes, Lindenmayer systems, or L systems, you can think of them as a really compact set of rules, almost like an algorithm or maybe even a kind of genetic code.
Okay.
And this code allows a computer to essentially grow these incredibly complex, non-repeating patterns from a very simple start.
So it's generative.
It's generative, exactly. And this formalization is absolutely critical because it gives AI a programmable grammar it can actually interpret, learn from, and even use to generate these structures itself.
It really drives home that these patterns aren't random at all. They're governed by defined principles, almost linguistic ones, that you can express algorithmically.
That's a perfect way to put it.
And the structure, this kind of ordered complexity, it's not just flat 2D patterns, is it?
Not at all, no. It extends into 3 dimensions, too. In 3D, you have specific polyhedra, like blocks, that fill space aperiodically.
So 3D versions of kites and darts, essentially.
Well, different shapes, but the same principle. These 3D structures often form what we call quasicrystals.
Quasicrystals. Heard of those? They're real materials, right?
Oh, yes, very real. Discovered back in the 80s. Imagine a solid material where the atoms are arranged in a perfectly ordered way, but that order, again, never quite repeats itself like in a traditional crystal.
So no simple repeating unit cell.
Exactly. It has long-range order. You can tell it's structured over large distances, but without periodicity. And this unique structure gives them really unusual physical properties.
Fascinating. And they're governed by similar generative rules.
Yes, extending this whole concept of a tiling language into higher dimensions.
Okay, so we've got the mathematical elegance down, these non-repeating patterns, this language of a periodicity. But here's where, for me, the story takes a really exciting turn. How are these abstract mathematical ideas, these languages, actually helping us build smarter AI?
Yeah, this is where it gets really practical.
What problems were AI researchers hitting? What walls were they running into? Where these tilings suddenly offered a key?
Well, it's quite fascinating how these abstract concepts are translating into concrete AI advancements. Let's call it the linguistic structure of Penrose tilings, gives AI researchers a novel kind of framework.
A new way of thinking.
Exactly. Inspiring new architectures, new ways to solve problems, especially in areas that, well, that naturally benefit from hierarchical structures or non-uniform structures, because these tilings also have this property called self-similarity.
Ah, right, self-similarity. Can you unpack that a bit for us?
Sure. Self-similarity basically means if you zoom in on a small part of the Penrose pattern, you'll see something that looks very much like a smaller version of the larger pattern.
Like a fractal.
It's got that fractal-like quality, yeah. The pattern looks similar, statistically speaking, no matter your magnification level. And this property, combined with the aperiodicity and this sort of natural hierarchical organization you see,
Right.
makes these patterns incredibly rich structures for AI to potentially learn from or even mimic.
So one big application area you mentioned is enhancing neural networks, specifically graph neural networks, GNNs. How does that work?
Right. So traditional GNNs often work well on regular grids or simple graph structures, but they can struggle with data that has really complex nested relationships or information that exists at multiple scales simultaneously.
Like social networks or maybe biological systems.
Exactly. Things with inherent hierarchies. But the hierarchical and multi-scale nature you find in 2D Penrose tilings is being explored to actually build better GNNs.
How? By structuring the network itself like a tiling.
Sort of. By constructing the graph structures based on these tiling principles, researchers can create networks that are, you could say, naturally suited for learning from data that has those built-in hierarchical relationships. This might lead to more effective ways of doing things like hierarchical pooling or multi-scale analysis within the network.
Interesting. And it's not just GNNs, right? You also mentioned large language models, LLMs. How do non-repeating patterns help there?
Well, this is potentially a really significant development. Think about the huge number of parameters, the weights inside a big LLM.
Billions,
Yeah.
sometimes trillions.
Right. And traditionally, the architectures often assume a kind of uniform interaction structure, but the actual dependencies between parameters, the way information needs to flow, might be much more complex and non-uniform.
Okay, I see where this might be going.
Penrose-like structures, with their inherent multi-scale organization and that non-repeating nature, they offer a potentially revolutionary way to structure those weight matrices, to encode those complex relationships more efficiently.
So instead of a simple grid connecting parameters, you use something more like a Penrose tiling structure.
That's the idea being explored. It's like building the LLM's brain not on a uniform lattice, but on something more organic, more fractal-like. This could allow it to capture nuance far more efficiently.
Which could mean smaller models, faster training.
Potentially, yes. More efficient models, capturing complex, non-uniform relationships better, maybe making these powerful tools significantly more accessible or performant. It's an active area of research.
Okay, let's shift gears a bit. Material science and drug discovery. You mentioned quasicrystals earlier. It sounds almost sci-fi using AI to find these things. Are there big hurdles, though? Like, is it easy to actually make these materials based on AI designs?
That's a very fair question. And you're right, one of the biggest practical challenges, especially in material science, is precisely controlling the synthesis. Making these quasi-crystalline structures reliably and at scale is definitely tricky.
But AI is helping with that part, too.
It is. AI, particularly deep learning, is becoming really instrumental in just discovering and analyzing these 3D aperiodic structures, like quasicrystals, in the first place.
How so?
While identifying them from experimental data, like diffraction patterns, is incredibly challenging for humans because the patterns are so complex, not repeating simply. Machine learning models are being developed that can spot and classify potential new quasicrystalline phases much faster.
So AI does the heavy lifting on the analysis front, speeding up discovery.
Exactly. It accelerates the discovery pipeline for finding new materials that might have unique electronic, magnetic, or mechanical properties because of their structure.
And it's not just finding them, right? You hinted AI could help design them, too, using the generative rules.
Absolutely. The principles for generating these complex rule-based structures, like the L systems we talked about, are relevant for generative AI. The same rules that describe a 3D Penrose tiling could inspire generative models to design novel molecules or materials with specific desired functionalities.
It's like the AI is learning the grammar of these structures and then writing new molecular sentences.
That's a great analogy for it, yes.
Yeah.
Designing materials atom by atom, but following these complex, non-periodic rule sets.
Wow. And the applications keep branching out. You mentioned cryptography and security. That seems like a leap from material science.
It does, but it connects through the properties of complexity and unpredictability within a deterministic system.
Okay. How does that work for encryption keys?
So, generating good random numbers is crucial for strong encryption. A Penrose tiling, while perfectly deterministic, generated by rules, has a sequence that is highly complex and never repeats.
Ah, so it looks random locally, even though it's rule-based.
Precisely. And some researchers, particularly in areas like neurosymbolic AI,
Which tries to combine neural nets and symbolic logic.
right, they're exploring using a Penrose tiling generator as a deterministic but practically unpredictable source to create secure cryptographic keys. The complexity makes it very hard to guess the next part of the sequence without knowing the exact starting point and rules.
That's clever, using ordered complexity for security.
It's a unique blend of order and inherent unpredictability.
It really feels like these patterns have been speaking this hidden language, this language of complex order all along. And now AI is finally starting to translate it, or at least understand its utility.
That's a nice way to think about it.
It really makes you wonder what other hidden grammars might be out there in math or nature.
Absolutely. And just briefly, touching on creativity, the rule-based generation of Penrose tilings has inspired generative artists for decades.
Right, you see them in M.C. Escher-like work sometimes.
Exactly. And those same principles are now being applied in AI for procedural generation, creating complex, aesthetically pleasing patterns automatically in visual art, design, even game development.
So AI learning the art rules from the tiling rules.
In a sense, yes. Imagine AI designing, say, a fabric pattern that isn't just a simple repeat, but has subtle, non-repeating variations woven in based on these principles. Something that feels cohesive but is always slightly new.
Now, you mentioned that the applications using the 2D tiling rules in AI seem more concrete right now. What about the 3D rules, the quasi-crystal stuff? Is AI using those rules directly yet?
That's a good distinction. Currently, the direct use of the 3D tiling rules within AI algorithms themselves is still a more emerging area. The main focus right now is more on using AI to analyze and understand the 3D aperiodic structures we find, like quasicrystals in labs or nature.
So analyzing the output rather than embedding the generation rules directly into the AI architectures much.
Largely, yes. But this definitely raises important questions for the future, doesn't it? As our understanding deepens and as AI capabilities continue to grow.
You'd expect more direct integration.
I think we can expect to see their generative rules being more directly incorporated into the design of intelligent systems, perhaps for things beyond just materials. So yeah, get ready to keep unpacking this really unique intersection of math and AI.
So let's try and wrap this up. What does this all really mean? We've taken quite a deep dive today into how the rules, the grammar of 2D and 3D Penrose tilings are, well, they're far more than just some mathematical curiosity.
Right. They really constitute a kind of formal language, a language capable of describing a very unique form of order, one that's intricate but non-repeating.
And this linguistic framework, with its built-in properties of periodicity, that self-similarity we discussed, the hierarchical organization, it's genuinely proving to be fertile ground for AI innovation.
Yeah, the applications are surprisingly broad, from enhancing how neural networks like GNNs and maybe LLMs are built,
To speeding up the discovery and even design of new materials, new drugs, by analyzing and generating quasicrystal-like structures.
and even strengthening cybersecurity through complex key generation. The utility of these patterns is, well, it's pretty undeniable at this point.
This deep dive really shows how concepts that seem purely abstract, purely mathematical, can suddenly become incredibly powerful tools, pushing the boundaries of what AI can actually achieve.
It really does. And it leaves us, and hopefully you, with a really important question to think about. If these abstract, non-repeating patterns can be formalized into a language that AI can understand and use, what other forms of hidden language might exist out there in mathematics and physics and biology, languages that could potentially unlock entirely new ways of thinking about intelligence and discovery?
What other unexpected connections are just waiting to be made between fundamental principles we already know, maybe, and future technological leaps?
Exactly. It's a pretty fascinating thought, isn't it?
It really is. Makes you wonder what's next.